All right, hello. Today is September 24th, 2014, and this is the new astronomy. It's part 3 of 4 of part 4. So today we're going to go over chapters 51 through 56 and then have an open discussion period. So we might end up talking about chapters much earlier, whatever's on your mind. So I wanted to review for next week. There's going to end up being 2 hangouts next week. There'll be one video file for actually going through chapters 57 through 60 next week, and there'll be a separate. Just mute yourselves there. And then there'll be a separate hangout for discussion next week on top of that. Same day. They'll both be on. It'll be Wednesday. Okay, so for this part of the book, so just to review where we've gone with part 4 so far, or what's happened up to this part of the work. In part 4, Kepler is applying the physical idea that he's got of the solar power, and he's applying that to Mars. So the first thing he does was in those first 4 chapters, 41 through 44, he showed that Mars couldn't move in a circle. And he did that by showing that the distances were too far out at the middle, it had to come in, and also that using area to measure time made the planet go too slow here, meaning it should be brought in. So he's concluded Mars doesn't move in a circle. He then has the problem of trying to figure out, well, what can we do? How can we make Mars move? So he had adopted this idea of which we talked about last time. To show the picture again, if you can see it, you can click to the other view as well, the screen sharing view, if you'd like to. I think I'll put that up for YouTube. This was Kepler's first idea about how Mars could move in a non-circular orbit. He said, we'll put Mars on an epicycle that rotates uniformly, while the center of the epicycle moves non-uniformly. And because up top near aphelion, the planet's going to go slow, the epicycle will have time to twist it clockwise inwards. And overall, this will make the planet have an oval path of some sort. Oval means egg-shaped. Not an ellipse, not necessarily an ellipse anyway. So in what we did last week, we covered last week, Kepler has this hypothesis, and it's incredibly hard to try to implement it. So we had several chapters of him trying to put this into practice to see whether it worked or not, and he kept coming to the same conclusion. That was that it was wrong in a specific way. I'll show a picture of that. No, it's not that good. This hypothesis made the planet move too fast at the quadrants. So the circle was too far out. This new oval seems to be squeezed too far in. Kepler's thinking, well, must be something in between them. But before he makes a new hypothesis, he takes care of some things, and that's what we're going to do in these chapters. These 6 chapters are taking care of wrapping up a few loose ends, finding some Mars distances, being more certain about the eccentricity and some things like this. And then the last chapter we're going to talk about is where Kepler has an insightful breakthrough based on that number that I hope everybody had put up on sticky notes in their bathrooms or wherever to remind themselves of it. So the first thing that Kepler does with these ones is, and I'd like to go ahead and read the beginning of this chapter, chapter 51. Kepler says, or actually, does anyone else like to read that first paragraph of chapter 51? If so, just unmute and go right ahead. All right, well, I think I'll go ahead and read it then. Kepler says, well, I am thus celebrating a triumph over the motions of Mars, and fetter him in the prison of tables and the leg irons of eccentric equations, considering him utterly defeated. It is announced in various places that the victory is futile, and war is breaking out again with full force. For while the enemy was in the house as a captive, and hence lightly esteemed, he burst all the chains of the equations, and broke out of the prison of the tables. That is, no method administered geometrically under the direction of the opinion of Chapter 45 was able to emulate in numerical accuracy the vicarious hypothesis of Chapter 16, which has true equations derived from false causes. Outdoors, meanwhile, spies positioned throughout the whole circuit of the eccentric, I mean the true distances, have overthrown my entire supply of physical causes called forth from Chapter 45, and have shaken off their yoke, retaking their liberty. And now there is not much to prevent the fugitive enemy's joining forces with his fellow rebels and reducing me to desperation, unless I send new reinforcements of physical reasoning in a hurry to the scattered troops and old stragglers, and, informed with all diligence, stick to the trail without delay in the direction whither the captive has fled. In the following few chapters, I shall be telling of both these campaigns in the order in which they were waged. I think that's a pretty fun way to describe this. So the first thing he does in Chapter 51, and hopefully you can see this on the screen here, it's on the webpage, it's the Chapter 51 webpage, is Kepler starts finding out, he's like, look, up till this point, he hasn't really determined that many distances of Mars from the Sun. He had a few spaced here and there in the early 40s that let him conclude it wasn't a circle. He definitely measured the aphelion, and he definitely measured the perihelial distance in Chapter 42 to get the eccentricity. But he's never systematically gone around and actually just found out how far away is Mars from the Sun. And that could be very helpful for, for figuring out what path it moves in. So these are the spies he's talking about. He's going to go and look for all these spies that are stationed around him, find out where they are, see what they know, interrogate them. So to do this, this is one of the two questions in the homework, is to redo there's only two homework questions in this section of chapters. First one is to redo one of the, it's basically just like, it's similar to this one on the page here, where we're going to, we redo Kepler's calculation of Mars's distance from the Sun, where he's got the Sun and the Earth. He knows where the Earth sees the Sun, so that's, he knows this angle, he knows this direction. He knows where the Sun sees Mars, so he knows this direction. That's from the vicarious hypothesis. He knows this angle, which is from the observation where the Earth sees Mars. So he's got these angles in the triangle, and therefore he can use the law of sines and figure out how far away is Mars from the Sun. So it's pretty straightforward. He does it all these different places, and it's important because he's able to, there's something very important about these distances, which, I don't know if you can see them. I'll put the other one up on the YouTube screen here. That the distances are equally spaced around his line of apsides. I mean, he considers the precision to be about 200 units based on inaccuracies of the observations, that it ends up coming out to making a distance uncertainty of 200 units. And none of these distances are more than 200 units away from each other. So that's suggesting to him that he got the line of apsides right. If he hadn't figured out, correctly, or at least mostly correctly, where the path of the orbit is split, these distances wouldn't keep being equal. So he's shown the path is symmetrical. It's a good thing to know. Maybe the planet moved in a weird Paisley shape, or at least a slightly Paisley shape, or something like that. So he's shown that that doesn't seem likely. It's symmetrical. And that's what he does. That's really all there is to Chapter 51. He talks about how he does it. So that's that. That's what he does. 52 is also pretty straightforward. In Chapter 52, he just says, well, this proves that... Chapter 52 is where he says that he has finally proved that the mean sun is not how the planets work. I'll show the picture he uses for this. That makes some sense. Kepler says, look, the fact that these distances have been equal, along his line of apsides, he says, well, if we should have been using the mean sun, the right of these two lines, this would have been the line of apsides. And the distances can't be equal on both sides of this one. He gives the example right here. The distance to E and D are the same from the real sun. They're clearly not going to be the same distance from the mean sun's orbit. So he ends chapter 52, he says, so again, the faith that was pledged in chapter 6 and in many other places in this work, I have redeemed from all tincture of self-justification, and have shown that the eccentric of Mars cannot be referred to anything but the sun itself, and that in addition it is not only reason that stands with me, but the observations themselves, in my releasing the observations of Mars from the sun's mean motion and measuring them out by the apparent motion of the sun. So he believes that that's it, he said it, it's over. The mean sun is finally over here in chapter 52. 53 is another, we're not going to worry about that. It's pretty complicated, and he also sort of fudges his numbers and makes a number of mistakes, so don't worry about that one. Same thing with 54. It's really not all that exciting. He's doing something similar to what he did in chapter 42. He gets a slightly different size for the orbit of Mars. That's all. 55, just like in chapter 44, he said, okay, we know that the Earth doesn't move. We know that Mars doesn't move in a circle for the reasons of the distances and the speeds. In chapter 45, in 55, he says that the hypothesis of 45 is wrong. That this oval thing that we had made last time simply can't work. It brings the planet too far in, the distances are too short, and it makes the planet move too quickly at the middle longitudes. So the truth must lie somewhere in the middle. I'll see if anyone wants to read this part. Actually, the whole chapter is only 2 pages. Could anybody volunteer to read chapter 55? At least starting on the second paragraph.
Yeah, I can read it, Jason.
Go for it.
So you want me to start in the second paragraph? Okay, chapter 55. From the observations of chapters 51 and 53, and the ratio of the orbs of chapter 54, it is demonstrated that the hypothesis seized upon in chapter 45 is an error and makes the distances at the middle longitudes shorter than they should be. Indeed, I began to say this in chapter 51, but since more observations and more suitable ones were going to be provided to give evidence in chapter 53, from which at the same time something else was also inferred in chapter 52, the full demonstration was therefore postponed to this point. There is no need for verbosity, as the mean anomalies of all the examples appearing in chapter 51 and 52 let the distances be computed according to the hypothesis of chapter 45 and the ratio of the orbs of chapter 54 by the method I used from chapter 46 through chapter 50, and let them be compared to the distances of chapter 51 and 53 found using infallible observations. It will be apparent that the more we descend from the apsides, the more the computed distances are deficient with respect to the observed distances, a result quite the opposite of what we saw in chapter 44 above. For there the distances computed according to the law of the circle were longer than the observed distances at the middle longitudes, while here the distances resulting from the hypothesis that makes the planet's orbit oval are shorter. It is therefore obvious that the planet's path is neither a circle nor such as to make as great an incursion from the circle at the sides as does the oval that arose from the opinion of chapter 45 and was described in chapter 46, but takes a middle course. And if in turn, using the distances of chapter 45, you compute the observed positions of Mars, especially those which in chapter 53 stood at some distance on either side of opposition, the planet before opposition will fall too short forward, and after opposition too far back. This is most evident in the descending semicircle in 1589 and 1591, and in the ascending semicircle in 1582 and 1595. For in those places the oval of chapter 45 is 660 units too small, while the perfect circle is too large by the same amount. And this can have an effect upon the appearances of 20 minutes and more. Thus, David Fabricius was able to use his observations to charge my hypothesis of chapter 45, which I had communicated to him as true, with this error of having distances that are too short at the middle longitudes, writing at the very time when I was laboring to seek out the true hypotheses through repeated careful operations. He was, in fact, quite close to arriving at the truth before me. And since the perfect circle errs the same amount in the opposite direction, it is thus argued rightly that the truth is in the middle between the two. Moreover, the equations computed for physical causes in chapters 49 and 50 gave the same testimony, namely that the luneal cut off from the perfect semicircle ought to have only half the breadth of the one which the opinion of chapter 45 cuts off. Therefore, nothing prevents our saying that the matter is most certainly demonstrated, that the opinion of chapter 45, in remedying the excess of the perfect circle, falls into the opposite defect. So the physical causes of chapter 45 go up in smoke.
Right. So I guess he spoke for himself there.
Sorry, I'm.
Okay. So what Kepler, I mean, I guess he said it. That the truth has to lie somewhere between these two hypotheses, the oval of 45 and the circle. He gave a specific number. He said that the oval of chapter 45 is 660 units too small, while the perfect circle is too large by the same amount. So this is where he's referring back to chapter 51 and the distances that he has to have a more specific idea about how he ought to be changing things. And at this point, he where should he go next? So could I get somebody now first off, I hope everybody remembers that number that we were looking at, because the width of the luneal was 858, which means that half of its width would be 429. Now, in the chapter we just read, I know Kepler had said that it was 660 units. Let me just switch the camera over here. Let's just figure out what the 660 units turns into also. So change your view over to the page here. He had said in so let's just take a look at how much 660 units is. So 660 units, that was if the Earth's orbit is 100,000. So 660 units are when Mars's orbit is 152,350. That was the value that he got in chapter 54. If we want to express that in terms where the Mars orbit is 100,000, we've got a little bit of math to do. So 660, if we multiply both sides by 100,000, And these two cancel, and we'll have just our number that we want over here. So we can use our calculator, say 100,000 times 660, divide by 152,350. That equals 433. So this came from measuring the distances of Mars on the orbit precisely. The other number that we had was the 858, was the lunule in chapter 47 when he used the ellipse. Half of that would be 429. So these are the amounts that Kepler would hope to bring Mars in from being on a circle. That would make it about half as far in as the hypothesis in chapter 47. And that's what he'd like to, if he could find that, if he had some way of doing it. Because, I mean, Kepler's not just going to, throw in a number and try to make things work. Everything's physical for him. So could I get a volunteer to read the first couple paragraphs of chapter 56? Any volunteers?
Hello?
Hello.
Hi. Yeah, I can do it.
Hey, Emma. All right.
Just the first few paragraphs, you said?
The first two.
Okay. The breadth of the lunule of chapter 46 above, born to us out of the opinion of chapter 45, which instructed us to cut it off from the semicircle, this breadth, I say, was found to be 858 units, of which the semi-diameter of the circle is 100,000. But then, by two arguments, by no means obscure, which I have already presented in chapters 49, 50, and 55, I concluded that the breadth of the lunule is to be taken as only half that, namely 429, or more correctly, 432, and in units of which the semi-diameter of Mars is 152,350, nearly 660. I therefore began to think of the causes and the manner by which a lunule of such a breadth might be cut off. While I was anxiously turning this thought over in my mind, reflecting that absolutely nothing was accomplished by chapter 45, and consequently my triumph over Mars was futile, quite by chance I hit upon the secant of the angle 5 degrees 18 minutes, which is the measure of the greatest optical equation. And when I saw that this was 100,429, it was as if I were awakened from sleep to see a new light, and I began to reason thus. At the middle longitudes, the lunule, or shortening of the distances, is greatest, and has the same magnitude as the excess of the secant of the greatest optical equation, 100,429, over the radius 100,000. Therefore, if the radius is substituted for the secant at the middle longitude, this accomplishes what the observations suggest. And in the diagram in chapter 40, I have concluded generally that if you use HR instead of HA, VR instead of VA, and substitute EB for EA, and so on for all of them, the effect on all the eccentric positions will be the same as what was done here at the middle longitudes. And by equivalence, in the small diagram of chapter 39, alpha chi will be taken instead of the lines alpha delta or alpha
Iota.
and alpha mu or alpha
Epsilon.
epsilon or alpha lambda.
let's take a look at that picture. I would like you to read the next paragraph, but first let's take a look at the picture. So I've got this up on the screen here. Um, Actually, let me do it so I can point at it. So these are kind of maybe small to see, but this is this epicycle that Kepler had. So from the Sun to, this is the mean distance of Mars. Yeah, the radius of its orbit comes out here to beta. The farthest it could ever be is gamma. The closest it would ever be is zeta. So from the Sun there, that's the closest Mars might be. So the size of the circle is the eccentricity of Mars. I'll show the other picture too. But what he's saying was, going back to chapter 39 and 40, he's saying is instead of a distance being, if Mars would have been this far away from the Sun, alpha to delta, he's saying bring it over here to kappa instead. Instead of, if you set your compass, the metal part here and the pencil here, it'd come up here to iota. He's saying instead of alpha iota, it'll be alpha kappa. Here at epsilon, if we took our compass and spun it over, we'd get lambda. Kepler's saying if instead of lambda, we had mu. That's the change he's proposing. Let me show it on the other diagram. Those letters there. And now this, if people remember this from chapter 40, he was looking at this there as well, where he's saying if Mars would have been at h, at this distance from the Sun, instead what he does is he takes any place that Mars might have been, draws a line through the center, through the diameter, right? He's drawing a diameter, and then he drops it perpendicular to it. So if you can see this point here from the Sun to point R, this is a 90-degree angle. Kepler's saying is let's use RH for the distance to Mars instead of AH, instead of the Sun's distance. Or over here, if the planet were, if we were considering this point V, instead of being this distance from the Sun, we'll use this distance from the Sun. So that's what he's let's actually look back at this, where this 100,429 comes from, before we move ahead. So let me switch over to there we go, over to the paper. Is this showing up mirrored, by the way, or does that look right when you're reading it?
No, that looks right.
Okay.
Oh, it's mirrored.
So he's saying, look at it on the, click on the other feed at the bottom.
Okay.
So, this Hangouts mirrors things, so you look like you're looking in a mirror, so you don't get weirded out. The angle that Kepler talked about, he said the secant of, first off, does everybody know what a secant is? Let's go ahead and review some trigonometry terms. I made that too big then. I'll come back down. Let's just take this portion here. Okay, so here's a portion of a circle. If I take any spot on it, like right here, and I draw a line out to it, so I've got a certain angle. I think that some of these we're pretty familiar with. So what's this line called? This is our angle.
That's your sign, right?
Pardon me?
Sign?
Yeah. The green thing's called the sine. Now, we have a word cosine. Kepler, he never uses the word cosine. He doesn't use them. He does have this length, though. This red length. Does anybody know what that's called? Nobody uses this anymore. But Kepler uses it a lot. Okay. This thing's called the versed sine. So it's basically 1 minus the cosine. I mean, today we would say, okay, yeah, that's, today we would say, this is the cosine right here, this green thing. And so Kepler will often, he'll use this versed sine thing. There's a couple more things that we can draw. If we take if we draw a normal to draw the tangent here. I'm drawing that pretty tangent here. Okay, looks good. Whoops, didn't touch it. Okay. There's another length that Kepler uses, and it's this one here. This blue length. Does anybody know what this blue length is called?
Is that the secant?
That's the secant, right.
You stop what you're doing.
So the secant is like the opposite of the cosine. A cosine, well, first off, we got this blue thing here. This is the radius of the circle. This is like our 1. That's the radius of our circle. So the cosine, we got a right-angled triangle here. The cosine is, it's the side here next to the angle, when the radius is the hypotenuse. A secant, this triangle here, where we go from the center of the circle to the point on its circumference to this point over here, this triangle here is similar to this green triangle. You see why? That's a right angle. That's a right angle.
Because it has two of the same angles. Well, it has all the same angles.
Exactly, right. Yeah, both this green triangle and the larger blue one, they both have got this same angle here, and they both got a right angle. So it's the same. If you took this blue angle and flipped it over, it would be like a bigger version of the green one. So the secant is like the opposite of the cosine. The secant is when the radius becomes the side, and we make a new hypotenuse. The cosine is when the radius is the hypotenuse, and then the cosine is this edge next to the angle. The secant is when we make the radius the edge next to the angle and make a new right triangle. So this is the secant here. So what Kepler is saying is that he's talking about, he says that he said for 5 degrees and 18 minutes, which is the greatest optical equation. Let's take a look at what this optical equation is here. So back to his picture here. Here's the center. Here's the sun. Let's take a look at a couple of spots here. Like to look at that spot. Look at this spot. So what I'm going to do is I'm going to make I'll make the radius the thicker black line. This is 100,000 for Kepler. This is 100,000 for Kepler. We can figure out the size of the other parts of these triangles. Now, as far as this greatest optical equation goes, let's take a look at let me pull out this one triangle here. So from the center, out here, 100,000, and then back down to the sun. The greatest optical equation is the difference between where the sun sees Mars and where the center sees Mars. So the angle Kepler's talking about is in here. That would be that optical equation he's talking about, the 5 degrees and 18 minutes. I actually forget which one of these it is. But if we do this, so what he's saying is when he says the secant is 100,429, he's saying that in the triangle, the hypotenuse is 100,429 when the edge next to the angle is 100,000. Meaning that in this triangle, if this distance, 100,429, if we used 100,000 instead, how much shorter would it be? It's pretty simple, right? The difference is 429. So what Kepler is going to do, what he does, draw this up. He says, let's take this triangle as our example, but we'll do it everywhere. If only we could make the distance from the sun not be this length here, but be this shorter one. If we could make it, instead of being 100,429, if we could make it only 100,000, we'll have the right distance here at the middle longitude. To apply that idea everywhere, Kepler makes the diametral distances. So here's a spot, right through the center. Okay. Now we connect those spots with the sun. And then we draw up a perpendicular, the diameter. Use those letters that Kepler, oops, let me write those letters on. What does he call it? H. Okay. Calls this an H. Calls this point R. This is Z. Sun is A. Center is B. So what he's going to do is where Mars might have been this far away, AH, he's going to take this distance HR instead. So he's going to make this red distance the distance that Mars is from the sun. Maybe you can see how that's analogous to the initial triangle, where instead of the hypotenuse, he's taking the base of the long side here of the right triangle. Here again, he's making a right triangle that goes through the center. And instead of this long hypotenuse, he's going to make the red length be where Mars is from the sun. So to do that, let me grab something used as a compass. I want to draw this one pretty accurately. Yeah. What I have to do. Well, good as it's going to get. So he takes this distance HR. You see I'm creating that distance. I take that distance from the sun and I spin. Okay. I make this new spot right here. So Kepler's saying if I can put Mars right here, it'll be at the right distance. Over here, for this example, let's do the same thing. Okay. We want to use 100,000 instead of, I know my hands are in front of the camera here, but we want this distance of 100,000, but we'll take it from the sun. So, you know, it brings it in some way. It's brought closer in on the side. by about 429. So this is Kepler's idea. These are the diametral distances. He had used these back in chapter 40. He'd used these back in chapter 40 when he was talking about the problems of trying to add up all the distances to be the area. I don't know if people remember.
Yeah, it was the conchoid, right?
Exactly. Yeah, let's put up that picture of that conchoid here. Oops, that's not it. There we go. So yeah, if you remember from back from chapter 40, Kepler was putting, these are like this is the sun and this is some spot on the circumference of the circle. He had all these distances of Mars from the sun. That's the main conchoid. Then he's got this dashed conchoid here. These are the diametral distances. The way he had created this other conchoid back in chapter 40 was by doing exactly what he's doing here. And he went through this whole thing back in chapter 40, where he said instead of using the distance from the sun out here, he'll use this distance over to here instead. The reason he said that this will end up adding up to the area is that from points H and V, both of their distances to the sun is more than the diameter, but both of their distances, their diametral distances, add up to just be the diameter. So if you used a whole bunch of those, you'd just be adding up. He goes through why it would be the same as this Archimedes way of adding up a bunch of triangles and getting the area of the circle. The important thing about it being that let's see here. Well, what he does with it is where did I just put down the there it is. And this is the second. There's only two. For these chapters, it's real light. You skip 2 chapters entirely. There's only 2 questions. But the second one of the second homework question is to go ahead and calculate out what this diametral distance is, and then compare that to the distance that you calculated Mars should be from the sun based on observations. So you're going to redo a calculation from chapter 51, where he says, how far is Mars from the sun? I can know that from my observations. And then you're going to check out this diametral distance hypothesis of chapter 56 by calculating from out on the eccentric to this perpendicular drop spot. And you'll see, does it give us the same? He ends chapter 56 with a big table where he compares the distances from chapter 51, where he just went all around the circle and got a bunch of distances. He compares them with the distances based on, calls it reciprocation, these diametral distances, and they come out being the same. So Kepler is, this is Noy to not sit in front of that. Kepler is very happy about it. Just to read the very last chapter on this, last paragraph in this chapter, he says, as you see, therefore, the distances measured on the diameter found a priori in chapter 39, meaning he had discussed it as just a concept in chapter 39, but now they are confirmed by closely spaced and very reliable observations throughout the entire perimeter of the eccentric. And that's where these chapters leave off. He's got this construction that creates the right distances, and it works. And you better believe that Kepler is not at all he doesn't feel very complete or fulfilled by this, because why would the planet drop a perpendicular onto a line drawn through the center when there's nothing at the center, and then take that distance and then be at that distance from the sun? It's totally geometrical right now. There's nothing physical about it at all. And so where this leads to with the next 4 chapters, there's only 4 more chapters in part 4, it leads to him talking about what the physical power could be that moves the planet towards and away from the sun. And he tries to figure out if he can come up with if there's a potential physical force that would cause the planet to come in and out in exactly this way along the diametral distances. And so that's where he's going to go in the next 4 chapters. So let's start by seeing if there's any questions on anything we just talked about right now, and then go through that a little bit, see if there are any, and then otherwise can take questions on anything. So, is there anything about what we just covered right now?
Does he set up those distances in order to create a shape?
You mean, does he like see what shape the distances of chapter 51 make?
Yeah. Or in chapter 56.
Oh, yes. Yeah, he will. Well, here's the thing, is that he's not... on the web page there is an animation which cheats. It's a little bit... I'll show the picture. You can see that. This is super exaggerated. Can't even see that. Here, I'll put on the screen sharing thing. Let's switch the view. So this is the shape of the orbit. He realizes later in chapter 58 that he calls it cheeky or puff-cheeked. It looks kind of like it's got its cheeks puffed up or something, and then it's got its chin at the bottom. So he is going to make a slight change to this. His first way, as you can see, let me pause it. His first way of applying this distance. I think I should do this on the screen, even if you can't quite see it. It's still better, I think. Yeah, need better cameras. You can kind of see it. So this is where the planet would have been. Draws a line through the center. I didn't draw the whole diameter, but drops a perpendicular up from the sun. Takes this length between these 2 points. Sets his compass equal to it. Puts the metal part of his compass right here in the sun. Spins the compass around until it hits the spot here on the line coming from the center. And he says, that's where I'll put the planet. It doesn't bring it in exactly 429, but the difference is small. This eccentricity is obviously incredibly exaggerated. Whenever he's making these shapes, he always does it by numbers. I mean, Mars's eccentricity is so small, even though Mars is pretty eccentric among the planets. The eccentricity is so small that if you draw, like what we know today, the ellipse for Mars is shape. If you draw that and you draw a circle and you ask people to tell them apart, you basically can't. So when he realizes it's got this puffy look, it's not because he made a flash animation and saw what the whole thing looked like. He found that the distances were farther out at top than at the bottom. Does that address what you were wondering?
Yep.
Okay. Okay. Any other questions on this part? I recognize not everybody's read these chapters, but if you have any questions just from this overview. Otherwise, we can switch to any questions. Just to reiterate, with these, the work for these chapters is it's not very intense. These ones are a little bit. They're definitely way easier than 45 through 50, which are, they're among the toughest chapters in the book. They're very involved. So Okay, any questions about other parts of the book then? Or thoughts or reflections too, or what are you thinking? Don't be embarrassed if you're wondering something about part two. All right, let me turn the YouTube thing off then, and let's see what we've got. YouTube viewer, I'm glad the trigonometry was helpful for you, and we'll see you next week.